Today, my name is Ashley Jubal. I am the IT Security Manager from Griffith University. If you need anything or have any questions about what's going on today, come and ask me, please. I'll also be a part of the speed debate panel this afternoon, and I am sure to make a fool of myself, so don't hold that against me. Our next presenter is Michael Gianarakis.
That's it. Yeah, you got it right.
I told him I'd make a mess of that, but thank you. Michael is the Director of TrustWave Spider Labs in Asia Pacific. He's going to talk today on developing secure iOS applications, so please make Michael welcome.
Okay, all right. So I've got a lot of slides. I literally finished them this morning, so hopefully we get through it. We'll see how the pacing goes. But just quickly, a bit about me. As Ash said, I'm the Director of TrustWave Spider Labs for the Asia Pacific region. I also am one of the organisers of Sec Talks in Brisbane. If you are local, definitely check it out. It's a cool meetup. We do, talks, CTFs, things like that. And for those playing along, flat ducks. All right, so this presentation, it aims to give you a good overview of how to design iOS applications or secure iOS applications. It focuses on key security issues that we commonly find in iOS applications. It's not a guide to hacking iOS applications. I've done quite a few presentations on that topic. If you want, you can check it out online. There's a lot of material. But I really wanted to focus a little bit more on the secure dev side for this topic. So we'll just quickly go over an overview of the iOS attack surface, common iOS security issues, some secure design principles for iOS applications, and secure development approaches for key iOS security issues. So the attack surface. So this is like a really basic threat model of an iOS application, right? You've got your application, and it communicates. Typically, most applications communicate with a backend over a network, potentially even third-party services, Twitter, Facebook, things like that. Obviously it runs on an iOS device, and it can also communicate with other applications on the device through IPC extensions, from iOS 8 and things like that. So where are the issues in this, right? So obviously the network can be compromised, right? So man-in-the-middle attacks, pretty straightforward. Your backend potentially could be compromised. So server compromise, web attacks against any sort of web services that are supporting the application. Third-party services also potentially able to be compromised. The iOS device can be jailbroken or compromised, as well as other apps can be malicious. Obviously, it's less of an issue in iOS. They've got pretty stringent entry criteria into the App Store, but that's also a potential vector. And then your app, I suppose, as well. Obviously, less prevalent on iOS and the App Store, but certainly a big issue on Android. So understanding the risk profile of your app. So this is an important step that's often overlooked, but it really should drive the security design of your application. So when you're thinking about the risk profile and you're doing sort of your basic sort of threat modeling, so to speak, some of the key considerations that you should go over. What information is in the app and how sensitive or valuable is it to your organization? Who are the likely threat actors and what are they capable of? What are the likely attack scenarios that each threat actor is going to attempt against your application? What's your tolerance for risk? Both in the context of the application and organizationally, that's also a factor. And do you have any regulatory requirements, PCI, HIPAA, whatever, Cool. So common iOS application security issues. So these common issues are just based on my experience. I've done a lot of pen testing. I run a team that does a lot of pen testing on mobile applications, and working with a range of companies across all kinds of apps, like mobile banking apps and trading apps. The high security, like board paper apps, all down to like internal business apps, retail apps, games even. And so this is based on the common issues that I find on those on these sort of apps. Binary and runtime security issues are big. Transport layer security issues, so pretty well known issues, and data security issues, obviously, particularly with mobile devices, right? Anybody can pick it up and walk away with it easily. So those are the three perhaps most common issues, and these are the three issues that we'll be targeting. Because if you get these right, you're ahead of the pack already, right? So There's obviously a lot more to consider when it comes to the security of your applications, like back-end security and the web services that support it and things like that. But I mean, if we're looking at the client specifically, get those three right, and you're well and truly ahead of the pack. So before I get into the detail around some secure, fixing some of those issues and exploring some of the common issues there, I wanted to touch on some secure iOS design principles. So you should just be keeping these in mind, and if you understand these and take these into your design when you're designing an application and you're developing an application, even if it's not something I've kind of covered here, if you've got these in the back of your mind, you'll be thinking in the right way from a secure development perspective. So don't trust the client or the runtime environment, right? So, on mobile applications, it's very easy to be for the attacker to control the execution environment. So you want to make sure that you account for that, and definitely don't trust the client. I mean, that's age-old advice, right? Users will connect to untrusted networks, and we've seen that. They'll connect to untrusted networks, and they will click on stuff, right? So they'll click on any warnings and whatnot. So keep that in mind. And don't store anything sensitive on the device if you can. Obviously, there might be a business case or a use case to do it, and we'll discuss some of the things that you can take into account when you're doing that. But as a rule, try and limit what you're storing on the device if it's sensitive. So going into binary and runtime security. So as a reflective language, Objective-C can observe and modify its own behavior at runtime, which can be great from a development perspective. You can do swizzling and some interesting stuff there. But from a security perspective, it presents some problems. So it gives you the ability to create and call ad hoc classes and methods, and manipulate and abuse the runtime of the application. So it's really great for bypassing security locks, breaking logic checks, escalating privilege within an application, and stealing information from memory. Implementing runtime security checks can significantly increase the security of your application, make it harder to exploit any issues. So you should, and going back to the design principles, you should always assume that your application will run on a compromised device. If you come from that design standpoint, you'll design your application accordingly. So I just want to put a little bit in about Swift. Obviously, Swift is Apple's new language. Eventually, it will replace Objective-C. It won't be for some time yet. And I've done quite a few talks on attacking Swift applications, reverse engineering Swift applications, if you're into it. I won't go into that level of depth here. But just as a few key takeaways, it's less dynamic than Objective-C. So when I spoke about the dynamic, reflective nature of Objective-C and the stuff it allows you to do, it's a bit harder to do in Swift. And it's less flexible in Objective-C in some areas. But even though it's harder to perform the dynamic techniques that I just mentioned, it's still possible, particularly in mixed runtimes apps. So where you've got Objective-C code mixed in with Swift code, which is pretty common, right? So people that are maintaining applications that already exist, Objective-C applications, what they'll start to do, as they transition to Swift, is throw in discrete pockets of Swift and create a bridge runtime that has both, and that allows a lot more of those dynamic features to come into it. As well, the Swift team is planning on introducing some of the dynamic features of Objective-C, just so developers can use some of the patterns that they're used to. I think they'll probably do it in a safer way, but still it has the element of these issues that we're going to discuss. So, just a quick aside before I go into the detail, I want to talk about compromised devices, right? So generally speaking, iOS is one of the most secure operating systems available. One of the defining security features of iOS is the chain of trust. So every bit of code, from the bootloader right up to third-party applications, is all signed and approved by Apple. But as soon as you break that trust, all bets are off, and you can defeat all the security controls that are baked in. So some of the security issues discussed will require a compromised device in terms of exploitation. But as I said, you should always assume that that's the case if you're trying to develop a secure application. But this usually causes a lot of misunderstanding and confusion when it comes to discussing the impact of some of these issues. So like when we have client conversations and whatnot, and understanding what we should fix and how far we should go down this path. So just want to bust a few myths, right? So myth one, public jailbreaks are the only jailbreaks. I hear this a lot, right? I hear, but there's no jailbreak for version X.X whatever yet, so we're safe, right? But a few facts, public jailbreaks have been released for every, at least every point release of, major point release of iOS so far. There's a few ones where they've skipped over, but it's generally speaking, there's a public jailbreak. Not all users update to the latest firmware. It is certainly better than the Android ecosystem, but still it exists. Particularly on iPad, we see iPad users hold on to their devices longer, and then they hit ceilings in terms of firmware support. And iOS vulnerabilities are extremely valuable. There are many more exploits than just those that are given out by people for free on the internet, right? So jailbreaks are, incredibly sophisticated in a lot of cases, and a chain of like complex vulnerabilities. They're very, very valuable. Even Apple with their bug bounty program pays hundreds of thousands of dollars for them. So just because they're not publicly released doesn't mean they don't exist. Myth two, jailbreaks require physical access to the device. And so you hear this, well, someone would need to steal the device to compromise it. Not all exploits require physical access. So some of these are a little bit old, but there's some new ones there. So you got, historically you got the jailbreak me, right? The classic one, which you just visited a website and bam. Remote code execution via SMS, found by Charlie Miller. Nitro JIT vulnerability, so it's JavaScript engine vulnerability, also by Charlie Miller. Don't let him near your iPhone. And then more recently, Matt Solnick and Mark Blanchard did a talk on attacking the baseband control protocols that are mandated by carriers to get full over-the-air code execution on an unpatched device, at least at the time. Those guys are notorious for not patching their stuff. Yeah, and I guess the other point as well, going to the previous, some of the previous points I made, remote exploits are very, very valuable. So most of the time, jailbreak authors and like the public jailbreak authors will not release those, not only because they're valuable, but also because they tend to get patched quicker because they're more serious. So if you're trying to release a public jailbreak that's going to persist as long as it can, you're not going to burn remote exploits, but they do exist. Jailbreaks are always obvious to the user, right? So everybody thinks that, if Cydia is on the device, if it's not on the device, then it's not jailbroken, because that's Cydia, for those who don't know, is just a common app store that gets installed when you jailbreak a device. But if you're coming in as a hostile attacker, I'm not going to, and I want to compromise your device, or I want to compromise a series of devices, I'm not going to make it obvious, right? So that logic is kind of flawed. But if you are being targeted, or if you do have an exploit that you want to run wild, you're not going to do something as obvious as have an icon pop up to say, hey, you're jailbroken, right? Or I've compromised your device. Myth 4, and this is an interesting one, jailbreaking is Apple's problem. I get this a lot, but I think, and this applies more broadly than just iOS applications, but the security of your app and your data and your users' data is your responsibility, right? As a developer, as an organization, the security risk to your organization is your responsibility. You will be the one that suffers the impact if your app is compromised, and you should be actively managing the risk. You can't outsource your risk, right? And Apple won't secure your app for you. So Apple does a lot of great work around platform security, does a lot of great work around trying to force solid security practices onto app developers, but they won't secure your app for you. And myth 5, and this is an interesting one, you can't completely, you can completely protect against jailbreaking, right? So unfortunately, you'll never be able to completely secure an application. This is true for any application, not just mobile applications. But the idea is you need to raise the bar for the security of your app so that it becomes too difficult or costly to attack, right? So that's really what you're trying to achieve here. Perfect security is a myth. You're not going to achieve it. You just need to raise the bar. And that's the end of my rant. Cool. So going into some of the protections now against, what you can do to protect against a hostile runtime environment. So a simple and effective method of securing the runtime is to implement an anti-debugging control. So there may be reasons that you might choose to allow your app to run on a jailbroken device, and we'll talk about jailbreak checks in a second, but there should be no legitimate reasons for allowing debugging of your production application, right? Doesn't make sense. So can be implemented using a couple of techniques. So periodically monitoring the process state flag to determine if the process is being traced, and then terminating the process. There's a ptrace request pt deny attach that would prevent future tracing of the process as well, and that function called ptrace 31000 is how you do that. And then these techniques should be used in conjunction with each other to provide a more robust anti-debugging control. So you don't do one or the other, right? So you have the pt deny attach, but you're still monitoring the process state flag to see if it's being traced. Jailbreak detection. So jailbreak detection is a common security protection. There are multiple ways to implement jailbreak detection, but the two most common methods are a file system check and a sandbox integrity check. So file system checks test for the presence of files that are typically found on jailbroken devices. Some examples are mobile substrate, which is a hooking library, allows you to write patches, bash, SSH, things like that. You check for those sorts of files. And then one of the things to consider from a secure design perspective is you should ensure you check for multiple files. So you don't just do a basic one. Like a common one we see is you just check for cydia.app, right? So what happens if I delete cydia.app? I'm still jailbroken, right? Or I rename it, or I patch out the string in the binary. How do you check for that? So you should always check for multiple files, ideally checking for files that are going to break a jailbreak environment if you can. Use different methods. So a common one is file exists path, which as it suggests, checks if a file exists and returns yes or no, or is readable at file path. So if you're using multiple ones, it can protect you against just patching out file exists at path to return no every time or return false. So if you're making it helps to make a more robust file system check. The sandbox integrity check, as the name suggests, tests the integrity of the sandbox and making sure that the application is running inside it. It works by attempting to perform an operation that would not typically be allowed on a device that has not been jailbroken and the sandbox is still intact. So a common test is to attempt to use the fork function to spawn a new child process, but you can try access files outside of the sandbox or whatever else would come up with that sort of logic of, yes, I'm successful, or no, I'm not. And if it works, then it's compromised. If not, then it's all good. Check out, OWASP has a project called IMAS, and they have a bunch of security modules that you can drop into your application. The jailbreak check and the debug check are pretty good. It's a little bit old now, but the code is still relevant. So definitely check it out if you don't want to roll your own. And you can really go down a rabbit hole with this. And as I said, it goes back to sort of the threat modeling, right? Maybe you just want to do a basic version of this, right? Just to kill like some of the low-hanging fruit. Like if it's an application where I was able to develop a patch, and if that got easily spread around the internet, people downloaded it, to get. I'll give some examples. We had a very large fast food chain that we do work for, global fast food chain. And they had an application that allowed you to get free coffees, right, after a certain number of promotions or whatever. And you could easily patch that out to just give you a free coffee in the app and say, yep, I'm eligible for a free coffee. And you could put that patch up on the internet, and anybody that's got a jailbroken phone can download that and get free coffees. Now, this organization is huge, and they don't care about that, right? They don't give a shit. So, but another example was actually a local company. And they had an application, was for insurance, that uses all the sensors on your device to determine how good of a driver you are, and that has impacts on like whether you can get a reduction in your premium or other benefits. And because it's all being done on the client, if it's on a jailbroken device, you can mess with that completely. So that has a real business impact. So that might be a case where you want to invest a little bit more in these runtime protections, just because it has that business impact. So again, it goes back to the modeling. Inlining functions. So any sensitive functions, such as security checks, should be compiled as inline functions. Inlining functions complicates the attacks, and that involves, so for those who don't know, when you inline a function, it's essentially, the compiler essentially copies and pastes it anywhere that it's called, right? So rather than just having it, exist once in the code and then it gets called, basically, inlining functions will complicate attacks because you need, if you want to patch something out, you want to patch a check out, like a jailbreak check or a debug check, you have to find every instance that it's been inlined in the code and patch that out. So it can complicate it and just make it a lot harder to do. And so to do that, there's the attribute, always inline, so compiler directive that you can use to inline these functions. There are some nuances to that, right? So it may not always be honored. If you are doing that, you need to think about some of the other flags. So setting the inline limit compiler flag high enough to allow for the inlining of your code. Inlining is usually ignored if you don't have any optimization levels set, because it is considered an optimization. Don't use unit at a time, which is automatically set if you use optimization 3 and above. And don't use keep inline functions if your functions are static. Another more complicated but also very effective method of protecting against runtime attacks is address space validation. So anytime malicious code is injected to your application, it must be loaded into an address space, obviously. Validating that address space adds complexity to the attacker because it forces them to try and inject malicious code into the existing address space, which is valid, with valid code, or attacking the dynamic linker, which is hard, right? So there's a dynamic linker library function, DL address, that returns information about the address space of a particular function belongs to. So passing a function pointer of the class's method implementation that you want to validate into that function will basically return whether it's came from your app, one of Apple's framework, or some sort of unknown source, which is probably malicious. Going back to a little bit more of a design focus, simple logic checks, and this is a big one, right? So simple logic checks for security functions and business logics are easily susceptible to manipulation. So these are just some of the examples that we see all the time, right? I don't know if any of you guys are Objective-C developers or app developers, but this is just sort of a function signature called isLoggedIn, and it's returning true or false, right? So if I can patch that to always return true, have I got an auth bypass, right? Is jailbroken? Yes, right? That's a variable. I can easily change that on a compromised device. So if you're relying on the value of that variable, to be yes or no, you can easily flip that. Set debug flag, just another example. So here's an example for a mobile banking application in Australia from one of the big 4 banks. I'm not going to tell you who it is. And basically, they've got a jailbreak detector function, and basically they're doing some file system checks, so they're checking for the existence of jailbreak files or symbolic linking. That's symbolic links that are typically created when you jailbreak, and sandbox integrity. And basically, you've got here, basically those first 3 lines of me messing with the runtime to make it return false on all the checks. And then when you run them, they're returning 0, which is false, right? And then there's another way in terms of the logic, like thinking through the logic. The way that they did the file system checks were just to have an array of strings. I just change those to an empty array, and it also breaks the check, right? So again, thinking about the logic and how you can avoid simple logic, and it's also very common for getting checks. It's also very common in iOS applications, just the way that they're architected to have multiple stages of a workflow, right? So if you've got multiple stages of a workflow, we've got one function that does this, passes it off to another function to check it, passes it off to another function to log you in or whatever. You have to think about people being able to bypass that step, right? So all of this should get you thinking that securing client-side functionality can be hard. So if you've got anything sensitive in client-side functionality that's not a business imperative, you should try and shift it to the server if you can. Securing memory, so instance variables stored in Objective-C objects can be easily mapped inside the Objective-C runtime. Never store anything in memory until the user has authenticated the data and the data has been decrypted. obviously, because then you're not really encrypting it. Manually allocate memory for sensitive data rather than storing the data or pointers to the data inside Objective-C instance variables, and wipe sensitive data from memory when it's not needed. So here's an example of another, same banking app. I've got the PIN up there, tokens, your mobile number. That's actually my real mobile number. Call me anytime. All this other stuff, account name, account numbers, all that kind of stuff. So it's actually really hard to protect against, but just think about, the life cycle of these things and making sure that they're not staying in memory for as long as it needs to. Transport layer security. I've got a lot to go, but I'm running out of time, so we'll keep going. So users will connect their device to untrusted networks. Great. So if your app handles sensitive data, you should be encrypting all the traffic between the app and the back end. Pretty straightforward, right? Apple, since iOS 9, has implemented app transport security. And it basically forces all applications to use HTTPS to secure all network connections. And it forces all the latest protocol versions like TLS v1.2. They had mandated it, or had intended to mandate it from the end of last year, but it was extended because developers were having issues with it. And lots of issues with this, as you can imagine, come from third-party services, right? So there's some fine-grained control that's available to developers. So you can set per-domain exceptions in the info plist file. So you can include like certain subdomains. You got temporary access to loading HTTP resources if it makes sense, right? So you get some fine-tuned controls, but it's also possible with those controls to completely bypass it. Don't do that. I don't know if it's actually, once it comes in and there's a deadline, whether this will get you in trouble and you won't get accepted into the App Store. Maybe not. But even if it does, you shouldn't just allow all, right? You're defeating what's a pretty good security control. So Cypher Suites, anybody that's got a pen test background or has procured a pen test report will probably, no doubt, have seen 100 issues on insecure Cypher Suites. So you should, pretty standard stuff. Disable support for low and medium strength Cypher Suites on the server. You can also control this on the client to some degree. So if you're using NSURL session, you can specify the minimum supported TLS protocol using TLS minimum supported protocol property in the NSURL session configuration. But it's probably a bit redundant once you use ATS, right? Once it becomes mandatory. If you're using NSURL connection, there's no API to set the minimum protocol, but there's lower level C functions in the older core foundation framework, but it's not worth it, especially with ATS. Cert validation, you should always perform cert validation checks. Don't, always, even in dev, you should really do it. You get free certs, it's super easy. When using Apple's frameworks, it will accept a certificate if it's signed by CA that's in the trust store, right? Certificate validation checks are often overridden in development to avoid issues with self-signed certs because people don't want to deal with creating certs in development. Typically, this is encapsulated in a variable somewhere or some other simple logic, which, as we've seen before, can easily be subverted. This is again in a mobile banking app from one of the big four banks. And you can see there what I've highlighted is allow untrusted certificates is a yes or no flag, right? So and you can easily bypass that. And even the methods that check for it allows this insecure transport or untrusted certificate again as a yes no check, right? So very easy to patch out. To avoid having to do this, use valid certs in development. Just get some free certs. Let's encrypt whatever. If you do need to disable validation, ensure that the production builds essentially hard code the validation. So don't have those sort of switches in your code. And consider certificate pinning, which is my next topic. So they're great. Mobile apps are great candidates for cert pinning, as they only need to communicate with a small, clearly defined set of servers. Certificate and pinning greatly improves the security by removing the need to trust the certificate authorities, which, as we've seen many times before, is not a good thing. ISEC partners have a great library for implementing cert pinning, so you don't have to roll your own. It's at the SSL Conservatory on their GitHub page. It's important to remember, though, when you're pinning a certificate, that if you need to revoke the certificate, it will mean an app update. So you have to be careful with that, and that can get you into trouble if you don't plan for it. Data security, you're going to have to burn through this pretty quickly, but I think we're good. So there are two types of data security issues. sensitive data that's stored on the device by the application that was not secured appropriately by the developer, and unintended data leakage via system functionality, so caches and things like that. So insecure data storage. It's common to find sensitive data stored insecurely on the device. As a general rule, sensitive information should not be stored on the device at all if you can help it. So you should really consider the need to store sensitive information on the device. Generally, it's functionally and technically possible to not store the data at all. You store on the server, and you can just, like a web application, get it when you need it. Property list files. So don't store sensitive information using the user defaults, which creates plist files. They're unencrypted and can easily be retrieved from the device or backups. So I find all sorts of sensitive things in the clear and property list files: passwords, session tokens, sensitive configuration items, PII, if that's something you have to protect against. So definitely be careful what you're storing. SQLite databases. So avoid storing sensitive information in SQLite databases if at all possible. If you need to store sensitive information, encrypt the database using SQL Cipher. I think SQL Cipher may have been, oh no, there you go, encrypted core data as well. So if you are using core data, which SQL Cipher, at least when I wrote this, didn't support, I don't know if it does, the IMAS project, that OWASP project I mentioned before, leverages SQL Cipher, and it works with core data if you're using that. So it's there on their GitHub page. They have a bunch of modules. The data protection APIs. So if you need to write files with sensitive information to the device, not credentials, definitely don't write credentials into a flat file. Write files with the appropriate data protection attributes. So you've got, if you don't need to access the file in the background, so while the device is sort of locked or in the background, NS file protection complete if you're using NS file manager, and NS data writing file complete for NS data is the attribute you need to set. With that attribute set, the file is encrypted on the file system and inaccessible when the device is locked. If you do need to access the file in the background, use NS file protection complete unless open, and data writing file protection complete unless open for NS data. The file is encrypted on the file system and inaccessible when closed, like when the file is closed. But when the device is unlocked, an app can maintain an open handle to the file even after it's subsequently locked. However, during this time, it will not be encrypted, so you just need to pick the right one. Unintended data leakage. So sensitive data captured and stored automatically by the operating system. Often developers are unaware that the OS is storing this information. So there's a lot of data leakage that occurs. Background screenshot. Every time an application suspends in the background, a snapshot is taken to facilitate just a little animation that pops up. It's stored unencrypted in the app container and also a few other locations in the file system. This allows attackers to view the last thing that the user was looking at when the application was backgrounded. And people sort of say, well, isn't this a bit of a point in time thing? But if I've got persistent access to your device, I can just monitor that file and see the changes and get it. And so, over time, as you use the app and you're backgrounding it, or you get a call or something like that, you can generally find sensitive information. Here's an example. That's Evernote. That's the screenshot that's captured. That's not an actual device screenshot that I took. And this is a banking app. It's old version, but I put that up there instead of my banking app because I don't have that much money in my bank. So yeah, there's that. So to fix that, to address that, place content clearing code in the state transition methods. So there's state transition methods that are called when the app gets backgrounded. So application did enter background, application will resign active. That's when you get a call. The simplest way to clear the screen contents is just to set the key window's hidden property to yes. There's some sample code to do that, pretty straightforward. Be careful if there are other views behind the current views though, because they may become visible when the key window is hidden. So other methods, manually clearing sensitive info from the current view, pain in the ass, I wouldn't recommend it. Placing the launch image in the foreground. So there's a launch image that's the first thing that gets shown up when the app is loading for the first time. It hasn't been backgrounded. That's very common and that works well. A quick note, the ignore snapshot on next application launch will not prevent the screenshot from being taken. A lot of developers mistakenly think that. But yeah, so URL caching. So iOS automatically caches requests and responses for protocols that support caching, HTTP, HTTPS, and stores them unencrypted in a SQLite database. So make sure you configure the server to send the appropriate cache control headers, because that's how it works. You can also control caching on the client if you want. So if NS URL connection you implement, the connection will cache response delegate method. Code there, that's off Apple's documentation, so it's available. And then for NS URL session, you set that URL cache property to null. Logging, less of an issue since iOS 7. Pre-iOS 7, any app had access to the device logs and could view any data from that was logged from other applications. Even though it's been fixed since iOS 7, which is quite a while ago, still a good idea to make sure nothing sensitive is logged. You must, if you have to log sensitive information in dev for debug purposes or whatever, just make sure it's not pushed to production. So maybe define a preprocessor macro for nslog or whatever. The pasteboard, we're getting there. So cut and copy of bus patterns are tapped. Cache copy of that data is stored in the device's clipboard, which is accessible from every other application on the phone. And so if you have sensitive data, you should probably think about maybe disabling the copy paste functionality for sensitive text fields. Note that it's already done by default for password text field. So basically to do that, you subclass UI text view and override the can perform action with sender methods to return no for any actions that you don't want to appear. So when you copy and paste something, you see the little menu that pops up. Doing this for any action will just take it out of that menu, and that code will actually just disable that entirely. Autocorrect cache. To facilitate autocorrect, it keeps a binary keyboard cache containing ordered phrases of text entered by the user. You should turn autocorrect off in text fields whose input should remain private, and you do that by setting the text field autocorrection type to UI text autocorrection type no for all sensitive text fields. Crypto. Getting cryptography right in mobile apps is difficult. The primary challenge is key management. Most apps fall prey to storing the key with the lock. You need to use a key derivation function if you want to do that. Don't hard-code an encryption key in the binary. It's going to be easily retrieved by running strings, or if it's stored in a variable, do the runtime techniques I showed you before. Storing an encryption key in the keychain is not secure on compromised devices, so you shouldn't do that. You can access the keychain quite easily on compromised devices. On a compromised device, they can also be retrieved from memory, as mentioned, if you store them in variables. Wipe keys from memory when not needed, obviously. Use a key derivation function to derive a key to use to encrypt the master key. Should be based on a secret input, such as the user's password. Don't use a cryptographic hash of the key. Don't just use a cryptographic hash of the key. Use a sensible salt as well, such as identifier for vendor, which is like a unique UUID for your app. And quickly, I've got a couple of minutes, but I think I might make it. Shouldn't have to tell this group, but don't use any of those insecure algorithms for anything, really. I mean, other than stuff that's not related to sensitive information. And custom encryption algorithms, don't do it. I mean, that's age-old advice. Like, seriously, don't do it. Cool. So I've got a couple of minutes. So I do have time for QA. That's my Twitter handle if you want to tweet at me. And I do have a blog that I haven't updated in years, so I don't know why I'd bother putting it up there. But if anybody has any questions, I'm available. Got like 1 minute, I think.
Is everyone's brain fried?
Yeah, I'll try to put these slides up somewhere because I know I went through them pretty quickly. And if anybody's interested, yeah.
Can we please thank Michael? Awesome.